Hello students, I am Dr. Archana Sharma. Students, in previous lecture we learned about nth order derivative. How can we determine nth order derivative of a function by successive differentiation method? In this lecture we will also learn about nth order derivative. But in this lecture, I will explain you how can we determine nth order derivative of a function which is the product of two functions itself, and for this purpose we will use Leibnitz Theorem. According to Leibnitz Theorem, if we have a function which is the product of two functions, then we can find its nth order derivative, and its nth order derivative will be equals to u naught Vn plus nc1 into u1 Vn minus 1 plus nc2 u2 Vn minus 2 plus up to n so on, and last term will be un V naught. Here u is a function of x only and v is also function of x only, and this is the formula for nth differential coefficient of the product of two functions. We can understand this by this example. This example will help us to understand this better. Let y this is equals to sine log x square plus 2x plus 1, or we can write sine inverse y equals to twice log x plus 1. And we have to show this identity x plus 1 whole square yn plus 2 plus 2n plus 1 into x plus 1 yn plus 1 plus n square plus 4 into yn equals to 0. Here yn plus 2, this is the n plus 2th derivative of y, this is yn plus 1, n plus 1th differential coefficient of y, and yn, this is the nth differential coefficient of y. Let we have y is sine log x square plus 2x plus 1. We differentiate this with respect to x and we are getting first order differential coefficient, this is y1. This is equals to cos log x square plus 2x plus 1 into 2x plus 2 divided by x square plus 2x plus 1. We have used here chain rule, and after simplification we are getting y1 into x plus 1. This is equals to twice cos 2 log x plus 1. We can differentiate this again with respect to x and we get second order derivative. This is y2 into x plus 1 whole square plus x plus 1 into y1 plus 4y. This is equals to 0. This is an identity. We can consider this is an identity, and if we want to find an identity in terms of yn plus 2, then we differentiate n times this identity x plus 1 whole square into y2 plus x plus 1 y1 plus 4y by Leibniz rule. Here we can see clearly x plus 1 whole square into y2, this is the product of two functions. X plus 1 into y1, again this is the product of two functions. So we can use here Leibniz theorem and differentiating n times, then we get nth derivative of x plus 1 whole square into y2. Here x plus 1 whole square, this is v, into y2 we will consider as u. A term which has differential coefficient after some time 0, that way we will consider that term with v. Similarly here this is the product of two function x plus 1 into y. Here we will consider x plus 1 as v and y1 as u. Now we are using Leibniz formula, and after using Leibniz formula we are getting this identity x plus 1 whole square yn plus 2 plus 2n plus 1 into x plus 1 yn plus 1 plus n square plus 4 yn. This is equals to 0. Also we can determine the nth order derivative at x equals to 0 or nth differential coefficient at x equals to 0, or sometimes we can say that yn 0. For this we have to follow some certain steps. The first step, let's consider the function y, whatever the given function, then find its different order higher order derivatives, first order derivative, second order up to n so on. Then get equation in terms of y1, y2, y3 up to n so on. Find nth differential coefficient using Leibniz theorem. Then you find an identity by Leibniz and then put x equals to 0 in different order derivatives, first order differential coefficient, second order and up to n so on. And we got a recurrence relation also, which is the relation between n plus 2th derivative and nth order derivative. Then put n equals to 1, 2, 3, 4 up to n so on. In recurrence relation, getting in the equation number 5, and put n equals to 1, 2, 3, 4, 5 in a recurrence relation, then we got a pattern for yn 0. If even and odd values of n are following different pattern, then you can write the answer is separately for even and odd. We have this example, y equals to log x plus 1 under root 1 plus x square. We have to prove this identity and also find another differential coefficient at x equals to 0. For this identity, we first differentiate one time, second time, and then use Leibnitz theorem. We differentiate this one time, then after simplification we are getting y1 under root 1 plus x square, this is equals to 1. Given a function, this is equation number 1, and the equation which has y1, this is equation number 2. Then again squaring and again differentiating, we are getting an identity in y2 and y1. Now we can use here Leibniz theorem because this is the product of two functions in equation number 3. So n time differentiating by Leibniz theorem, and we are getting the identity in n plus 2th differential coefficient, n plus 1th differential coefficient, and yn. Then put x equals to 0 in equation number 1, 2, 3 and 4, and we are getting the differential coefficient, different differential coefficients at x equals to 0, as y is 0 has value 0, first order derivative this has value 1, second order derivative this has value 0, and up to n so on. If we solve this recurrence relation, this is the recurrence relation yn plus 2 at x equals to 0, this is equals to n square yn at 0. Now put n equals to 1, 2, 3, 4, 5 in this recurrence relation, and we can determine the value of third derivative, fourth order derivative, fifth order up to n so on at x equals to 0. If we analyze this pattern, then we can see that if n is even, it means even order derivatives are following same pattern, and if n is odd, then the derivatives are following another pattern. It means y2, y4, y6 all are 0. So if n is even, we can write nth order derivative is 0, and if n is odd, then y3, y5, y5, y7 up to n so on, they are following the same pattern, and if we see the pattern, we can write answer that if n is odd, the nth order derivative is 1 into 1 square